This is Conservation of Mechanical Energy, Part 2. We have derived our conservation law, but I'd like to discuss a caveat. Whether the mechanical energy of a system is conserved may depend on how the system is defined. Now, as far as defining a system goes, earlier I referred to a freedom that you have to choose which objects to include in the system and which conservative interactions to include in the system. And initially, for our example scenario, we made the maximalist choice to include everything possible inside the system. So we had these 6 terms in our mechanical energy, including all the potential energy that we could possibly include and all the objects as well. But what if we had made a different choice? What if we didn't include absolutely everything? What if we excluded some objects or interactions? What would our equation look like then? What would be the consequences? Let's find out. If the potential energy, either a gravitational or elastic potential energy, associated with some conservative force in the scenario is not included in the mechanical energy, then the work done by that conservative force must actually be included in with the work done by non-conservative forces. Essentially, if you don't include the potential energy in the mechanical energy, then that conservative force effectively behaves like a non-conservative force, and the work it does effectively becomes non-conservative work. Let's see some examples below of other choices for what to include or exclude from our mechanical energy for this system, once again, with cart A, cart B, and 2 springs, spring P and spring Q, moving along this track. So a series of examples here. Example 1, if we had, instead of including both carts, included just cart A and excluded cart B, that would also mean excluding cart B's gravitational potential energy. It would also mean excluding the spring potential energy here in spring Q. If we exclude that mass A, mass B spring interaction, we would have to exclude that mass A, mass B spring interaction if we're not including the kinetic energy of cart B here. Essentially, if we don't include cart B, that drops us down to 3 terms in the mechanical energy. We had to, in order to exclude KB, we also had to exclude UGB and the USQ there. But cart A is still going to be acted upon by the force from this spring when it collides with B. That force from this spring on cart A is going to do work on cart A. Now, it's a spring, so it should be a conservative force, but if we're not including the spring potential energy stored in this spring in our sum here, then the work done by that spring force on A effectively becomes non-conservative work. And so we're going to have to include it on the right-hand side of our conservation law here. Conservation law says that the change in mechanical energy of the system equals the work done by non-conservative forces. If we don't include USQ in this sum, then the work done by spring Q is going to have to appear here as if it were a non-conservative work. Next example, if we go even further and choose to also exclude the cart A earth interaction, that is, exclude the UG from our sum of terms in the mechanical energy, then that UG is kind of going to sneakily reappear over on the right side of our conservation law, because that force of gravity is still acting on cart A. It's still going to be doing work on cart A, but if we don't include the UG in with the mechanical energy, then the work done by that conservative force effectively acts like non-conservative work. So here it is, the work done by the force of gravity on cart A is going to have to appear on the right side of our conservation law if we don't include UGA in with the mechanical energy. We can go even further and also exclude the cart A wall spring interaction. If we don't include this spring potential energy in with the mechanical energy, basically if we cut the mechanical energy all the way back to being just the kinetic energy of this cart and nothing else, if our system is just going to be cart A and not cart B and not this spring interaction and not that spring interaction and not the gravitational interactions, if it's just cart A, then all the forces on cart A are effectively non-conservative. This spring force, that spring force from P, the force of gravity from the Earth, all those which should be conservative, they effectively become non-conservative forces, and the work that they do appears on the right side of the equation if we're not including their corresponding potential energies in with our mechanical energy. Let's go back to our initial choice where we had everything included, all 6 terms, and then instead choose to exclude just the MA wall spring interaction. So what if we go back to including everything except this spring interaction here? If we exclude that spring potential energy, so we have just the spring potential energy of spring Q, but not of spring P in our system. So we have these 5 terms instead of the original 6. Then, well, this spring force from spring P on the cart A, that spring force is still going to be doing work on A. That work will effectively become non-conservative work and show up over here on the right side of our conservation law if we don't include USP in with our mechanical energy. Now, all 4 of those options there, which we're free to choose, all 4 of those options give us what's called an open system, according to some definitions or some usages of the term open system. We'll talk about that a bit. Interactions not included in the system are sometimes called external interactions, which are always effectively non-conservative. That's what I've been discussing here. Any interaction that we remove from the mechanical energy effectively becomes an external interaction that does non-conservative work, and the force associated with it turns up as a effectively non-conservative force doing non-conservative work on the system. So sometimes a system with external interactions is called an open system because it may exchange energy with its environment. That's the key idea associated with openness. An open system can exchange energy with its environment, add energy to its environment, so lose its own mechanical energy or gain energy from the environment. The system's energy can change if it's exchanging it with the environment. That's an open system. And effectively, all of these options up here became open systems because this work on the right-hand side may be non-zero. That non-conservative work, or effectively non-conservative work, can change the mechanical energy. So the mechanical energy would not be conserved. The mechanical energy could be increased or decreased by this work done by forces that are either inherently non-conservative or that became external forces that acted like non-conservative forces. Long story short, if the system can exchange energy with the environment via non-conservative work, we call it an open system. And that's the case here, 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 and here. Just by defining our system differently, it becomes an open system that can exchange energy with its environment. And in those systems, the mechanical energy is not conserved. But if we go back to our original choice, our original maximalist choice to include all 6 terms, to include everything possible in the system, a system with no external interactions and no other non-conservative interactions is then called a closed system. So our original choice of including everything we could resulted in none of these conservative forces acting non-conservatively. And if there was no other friction or drag forces in the system, then there would be no non-conservative forces in the system doing work. Delta E would be 0. The energy of the system would be conserved. We call that closed in the sense that the system is not exchanging energy with the environment. It's closed to transfers of energy. The energy of the system is conserved in that case. I want to conclude here with a little disclaimer that some authors use the terms open and closed system differently than I'm using them here, so be on the lookout for slightly different usages.